Math 265A, Cuesta College. I'm Joe Vasta, and we're going to cover section 2.4, infinite limits. So we've been studying limits in chapter 2. Somehow limits are going to help us grab on to instantaneous velocity and a lot of other things as well. So, whoops. Trying to adjust it. There's a little orange haze out there from the fires. So let's go ahead and look at this picture here. This is a picture of a function. I suppose I should label it f. And this function has two vertical asymptotes. And those are those lines that look like dashed lines. And it's not really points on the graph, but it's showing you that this graph is going up and it's getting closer and closer to the wall, but it never touches it. And same with this graph down here. And so you probably saw some of these things in pre-calculus. Before you start freaking out, we don't really have to graph rational functions in this section. We just have to analyze them, analyze limits on them. So let's take a look at our first question. It says the limit of f as x approaches 2 from the right. Now remember, limits have been all about bugs. And this one, we're only going to use one bug. And we are approaching x equals 2. So here is, I'll put it on the x-axis, here's 2. And we are approaching 2 from the right. So here's a little bug. And you know, this bug's too big to be doing this, so I'll use the tip of the pen. And he's walking along this graph. And he's walking toward 2. So he's actually walking toward the wall, but he has to stay on the graph. So what is this y value going to eventually be? Well, it doesn't actually end up going to a particular y value. It ends up going up to infinity. So what we're going to say, and this is a positive infinity, what we're going to say is the limit equals infinity. Okay, so notice once again you're going toward 2, but where's the y value going? Up to infinity. Now, I want to let you know that this is notation. It's actually a certain kind of does not exist. So I'll write that down here. So it is a certain kind of DNE. So I only have room to write that right there. So it's a certain kind of does not exist. Okay, so we cannot just have just any limit that does not exist. We cannot label it as infinity, but when you see that the limit equals infinity, it is also a certain kind of does not exist. Let's go to the next one. You'll get more comfortable with this as we do more examples. That's why I have a whole bunch of examples. Now, let's move these guys out of the way. The bug is coming toward 2, limit of f as x approaches 2 from the left. So here's the bug here. He's approaching 2. Here's 2. Here's the x value of 2, and he's approaching it from the left on the graph. Where's he going to? Where's his y value going to? Well, his y value is not going to infinity, but it's going to negative infinity. And that also is notation, and it's also a certain kind of DNE. Now in the homework and on the test, on these problems, you do not want to put, for problem 1 and problem 2, just DNE. You have to actually be more specific and say infinity for 1, negative infinity for 2. Problem number 3. What is the limit of f as x approaches 2? Now we've got 2 bugs, and are they ever going to meet? No, well, this guy's going way up here and this guy's going way down there. So we cannot put infinity or negative infinity. This one gets classified as D&E. Some rationale behind that would be because these are actually different things. This is infinity, this is negative infinity. The first rationale is, as the bugs are traveling toward x equals 2, they're certainly not going to meet right before they step off. Okay, let's go ahead and do the next 3 problems. Maybe you can pause the video and see if you can do these 3 problems. We're approaching -1 from the right, then from the left, and then we're approaching it from both sides. So pause the video and write down some answers. Okay, limit of f as x approaches -1 from the right. Let's follow the graph. Here's -1, we're coming from the right, and where's our y value? Well, we're not coming up to a particular y value, but we are going where? To positive infinity. So I'm going to say this equals infinity. The next one, limit as x approaches -1 from the left of this graph here. So you're coming to -1 from the left, and the y value is going to infinity. Okay, now we could just go by the rule, well look, the right hand limit and the left hand limit have the same symbol, so therefore the limit is also going to be infinity. If you like the bug analogy, you could just say, look, those bugs are going, getting closer and closer to the wall, never going to touch the wall. But as they're going toward -1, they're going to the same y value. Well, it's not really a value, it's infinity. And so they're both going in the same direction. So once again, these, when you put infinity or negative infinity, it's a certain kind of D&E. These are called infinite limits. Now you can see why, because infinity is involved in some of them. And that is the deal. Before we move on, let's go ahead and do a definition. I'll put the definition down there. So it says x equals b, so this is a little abstract, is a vertical asymptote if and only if, okay, that means, well, we'll talk about that, if and only if infinity or negative infinity is involved with limits at b. Okay, so the if and only if means if x equals b is a vertical asymptote, then infinity or negative infinity, they're involved with limits at b. And then it also means if infinity or negative infinity, they're involved with limits at b, then x equals b is a vertical asymptote. We cannot really define vertical asymptote this precisely in a pre-calculus class, because that would mean that you would have to talk about what is a limit, and you would have to get into limits, and some pre-calculus teachers do that. When I teach pre-calculus, I don't have time to do that because there's so much in that class. But let's go ahead and now that we know about infinite limits, let's do a problem that comes right from the book. This is one I didn't assign, but it's like around the ones I did. This is one of those ones where there could be many possible answers. It says, sketch a possible graph of a function g together with vertical asymptotes satisfying all the following conditions. Okay, so the first condition is g of 2 equals 1. So they're saying this function has to go through the point 2, 1. So let's put a point there. The next clue right here, or whatever, what our condition that our graph has to have is f of 5 equals negative 1. So 5, negative 1 is on the graph. Okay, our next condition is a limit, and it says limit as x approaches 4. So there's a negative infinity there, so we know as you approach 4 there's going to be some sort of vertical asymptote. So there it is. So this is x equals 4. We should always label those. But look what it says here. It says the limit, and this is from both sides because there's not a little plus or minus up near that 4. So from both sides you're going to negative infinity. So you're coming down here from both sides. So we'll keep that in mind. Maybe we can even go like this. No, I don't want to finish drawing this until I get all the clues down. Okay, so that's what that means. We also see at 7 from the left and from the right, we have a infinity and negative infinity. So x equals 7 is going to be another vertical asymptote. So I'll draw that right here. And so as you approach 7 from the left, you're going to infinity, so you're going up. So you're going like this. As you're approaching 7 from the right-hand side, the limit is negative infinity, which means it's going down here like this. So those were all the clues that were given. And let's go ahead and draw the graph. So look at this. I'm going to make this thing go up. As long as it's a function, you have some freedom. Look at this. You can make it go like that. Whoops, missed that. And then this one right here, I mean, who knows? Maybe it goes like that. So there is a possible answer there. And that's how you do problems like that in your homework. Okay, so we're going to move on to some more kinds of problems here. We'll start renumbering here. So problem number 1 is I'll give you a function and I ask you some limits here. So we have a rational function. We're going to do these kinds of problems without graphing the rational function. See, if you can graph it, then it's just like the first problems we did in this section. We're going to show you that you don't need to graph these each time. So let's see what happens when you put 3 into this function. So when I put 3 into this function, I get 2 times 3, which is 6. And on the bottom, I get 3 minus 3, which is 0. Okay, so that's a bad thing. Okay, 6 over 0. And in the past, we would say, well, can we do some algebra to this? Can we reduce the fraction and make it so we don't have a 0 on the bottom? Well, we can't this time. We cannot reduce this fraction. So what we're going to do is I'm going to show you some notation. I don't think the book has this notation, but it's a really good notation. As you're coming toward 3 from the right, perhaps we don't want to put 3 into this function because of this. But maybe we want to put like, let's see, what is a number that's right to the right of 3? Now you might say, oh, that's 4. Okay, well, great. But maybe 3.1, or you can think, I'll put it up here, 3.0, 0, 0, 0, 1. Okay, so that's pretty close to 3, and it's to the right of 3 on the number line. So if you were to put that into this function, you would have almost 6 at the top. So I'll just keep the 6 up there. But on the bottom you would have, and you can do this in your calculator, 3 minus this number, which would be a really small negative number. So a really small negative number, I'm going to go and use this notation. Now it kind of looks like that notation, but when you see a 0 with a minus, and I do this in lecture, this means a really small negative number. And I'll abbreviate number. So think about this. If you have 6 over a really small negative number, you're going to end up getting a negative number. Okay? And you could actually plug that in your calculator. You can go 6 over, and then you can go 3 minus that. And so the really small negative number would be negative 0.00001. And so what you end up getting is if you go 6 and divide it by a really small negative number, and we want to just get used to this right here, this is going to give us a really, really big negative number. In fact, the closer you get to 3 from the right, the smaller that is, and the bigger this thing becomes in magnitude. So this is going to go to negative infinity. So that is the deal. Now, some of you might say, well, Joe, what do we do with this? Let's go ahead. I'm going to have to do what I did last time. I think I did it in this class, where I'm going to go 6 divided by negative, let's go 0.00001. What does that give me? Gives me a really, really big negative number. Now when I say big negative number, it has a big magnitude, so that's like negative 600,000. So this tells you, so I can go ahead, I could have put negative 0.0000000000001 there and gone 6 divided by that, and then this would it would be even a, shall we say, bigger magnitude negative number. It could be like negative 6 million. So this tells me when I have a number over a really small negative number, and this number is pretty much fixed, and this is going to negative infinity. So we could actually do limits of these creatures without seeing the picture, and that's actually a good thing to do, because once you get faster at this, it's a lot faster to analyze it this way than to take 5 or 10 minutes to draw a rational function. Let's go ahead and do the next problem. But before we do the next problem, this also tells you something. Okay, and then this is not part of the problem, but I'm going to just put it in anyway. F, which is this function, has a vertical asymptote, I'll abbreviate that, at x equals 3, because one of these limits cranked out a negative infinity. Let's go ahead and do the next one. I'm going to go ahead and put 3 in. Well, 3 is going to blow up the bottom, so why don't you put, like, I mean, maybe you're thinking in your head like 2.9999. And so basically on the top, I'm going to get something that's close to 6. So I'll say 6 over 0. But we don't really want to have 0. What is 3 minus 2.9999? Well, it's going to be a really small positive number. So the notation for that is that right there. So let me go ahead and put an arrow and say really small positive number. Now when I say small with negative number, I mean the magnitude. Okay. So when I have 6 divided by 0.00001 or 6 divided by 0.0000000000001, it's going to give me a really big positive number. So this limit happens to be infinity. Okay, And we already saw from the last one, I mean, this just confirms f has a vertical asymptote at x equals 3, and if you're thinking about the graph, from the right it's going down, and from the left it's going up along that vertical asymptote. Well, now, for this one, we really don't have to think too much, because as you are approaching 3 from both sides, we've already analyzed the right side limit and the left side limit, and they are not the same. So for this one, we're going to classify this limit as DNE. It's just a general DNE. It cannot be infinity or negative infinity for this problem. Okay, so let's go ahead and do part D on this. The limit of f as x approaches 2. So the first thing I always do is plug the number 2 into here. I do substitution. And so when I do that, I end up getting 2 times 2 on the top. On the bottom I have 3 minus 2. Well, this doesn't look like it's going to lead to problems. Looks like it's 4 over 1. We don't want to leave our answer like that on the test or in our homework. So the limit on this is 4. So I threw part D in there so we wouldn't forget that sometimes the limits are very quick to do. You just plug it into the function. So that is problem number 1. We're going to go ahead and switch functions on you. We're going to make the rational function look a little bit nastier. So here it is. And that rational function, it does look kind of bad. Before I start throwing numbers in there, I'd like to see if this graph has holes in it, meaning is there any canceling? Can I simplify this rational expression? And the first thing you might want to do is factor the top, factor the bottom. An x factors out of the top, and so this gives me x minus 2 times x. And an x factors out of the bottom. So this gives me x squared minus 2x plus 1, and of course that's going to be times x. Now the x's do cancel, and so I have a more simplified function that says x minus 2 all over. We could actually factor that. You don't need to because there's not going to be any other simplifying, but I'll write this as x minus 1 squared. So when we canceled that x, we found that the original graph G has a hole at the value that makes that undefined for this one right here is 0. So the hole's at 0, comma, something. So when we do these limit problems, and there's 5 of them, we want to use this simplified version and not this version, okay? Because this is going to be a lot easier to analyze this. So let's go ahead and do the first one. The limit of g as x approaches 0. So like if you put 0 in this first function here, you get 0 over 0. Well, when you cancel, you end up getting what? Negative 2. So I'm doing substitution now. We'll make an arrow pointing from here to there. So on the top I'm putting 0 in. 0 minus 2 is negative 2. And on the bottom I have 0 minus 1, so I'll go negative 1 squared. Well, if you go ahead and look at the bottom, that's just going to be 1, and our final answer for this is negative 2. And so we're done with part A, but this part A tells us that the hole is at 0, negative 2, and it's the case where the two bugs are going to meet, but they're going to fall in the hole as they meet. And so this graph has a hole in it, and all these limits we're going to be analyzing using the simplified version. Okay. So the limit as x approaches 1 from the right. Now notice, if you put 1 in there, you end up getting 0 on the bottom. So let's go ahead and see what happens. You put 1 in the top, you get negative 1. You put 1 in the bottom, you end up getting 0. And there's no simplifying this. We can't reduce anymore. So I would say consider putting a number that's close to 1, but on the right. So maybe a 1.001. So that's coming from the right. And you'll see that if you put that in there, the top's still going to be close to -1, so we'll keep that there. And the bottom's going to be, what you've got to decide, is it going to be a really small negative number or a really small positive number? Well, let's just think about this. 1.001 minus 1, so that's a tiny positive number, and then squaring it will always make it positive. So you've got -1 over a really tiny positive number. You can do that on your calculator if you want, but it's probably best to try to figure these out without a calculator. So if you've got like a negative number that's kind of fixed over a very small positive number, that's going to end up, when you press that on a calculator or whatever, giving you a very large, in magnitude, negative number, like -1,000,000 or something, because you've got the negative on the top. So this limit is going to be -infinity. So we see from this problem, not that we have to write this down, that G has a hole at x equals 0. We could actually say the hole is 0, -2. And then this one right here tells us that G has a vertical asymptote at x equals 1. Okay. Let's go ahead and do this one right here. The limit of G as x approaches 1 from the left. So if you put 1 in there, you still get -1 on the top or something really close to it. And on the bottom, you get 0. And if you're thinking of a number that's really close to 1 but on the left, maybe 0.999. So like 0.999 minus 1 is a negative small number. But then when you square that, it becomes a really small positive number. So we have the same situation where we have negative over positive, which is going to be a negative number, and then this thing will then become -infinity. Okay, let's go ahead and do part D. You're approaching 1 from both sides. Well, we've already done right-hand limit and left-hand limit, and they gave us the same symbol. So guess what? This is going to be -infinity. And we know, we don't have to draw this, but I'll go ahead and show you anyway. We know that at 1, the graph is going to look like that for a part of it. They're both going to be going down to -infinity when we're considering y values. Let's go ahead and do this last one. Limit of G as x approaches 3 from both sides. So let's see what we have here. Put 3 in there. On the top we get 3 minus 2, and on the bottom we get 3 minus 1 squared. So this one doesn't seem to be a problem. This one's going to be 1 on the top. 3 minus 1 is 2. 2 squared is 4. So our final answer is 1/4. And so this completes problem number 2. Let's go do some other problems here. Okay, so problem number 3, we have the secant. Really, the secant, there's a lot of ways of thinking of this. This is the 1 over cosine, so that's something you should know. And we are considering the limit as theta, so now things are in theta, approaches pi halves. Well, if you remember the graph of the cosine, so I'm not doing the graph of the secant, if you just remember the graph of the cosine, you know at pi halves, that is 0. So that's 0 at pi halves. So you have 1 over 0, and you can't cancel anything. So if you get a limit and it's just a regular limit coming from both sides and you end up getting something like this, then what you probably want to investigate is the limit as theta approaches pi halves from the right, and the limit as theta approaches pi halves from the left. And see if they give you the same thing. I'm going to go ahead and do this. And there's a few ways of doing this problem, by the way. So if you're thinking, wait a minute, Joe, I've got a better way of doing this, I'll explain another way that some of you would like and some of you would say, no, but don't like that. Okay, as you're approaching pi halves from the right, you have 1 over cosine of pi halves is 0, but a little to the right of that, it's going to be a very small negative number, the y value. Okay, so I'm going to go like this and say a very small negative number. And when I have 1, a positive 1 over a negative number, or a very small negative number, this gives me negative infinity. Okay. It's not my final answer. I'm using these to analyze this one. And now when I have the one down here, I'm approaching pi halves from the left, and I'm looking at this one, the 1 over cosine. I have 1 over cosine pi halves is 0, but a little to the left would be a positive y value. Okay, it's a very small positive y value, which gives me 1 over positive 1 over a very small positive value, which is infinity. So all of this just to get, I don't know why I circled that one and boxed that one, but this is my final answer. These guys do not match. I shouldn't put an equals to. We're just going to say this does not exist here. And so doesn't this mistake I did here. No one's ever going to see it. There we go. Except the people watching the video. So D and E is the answer. Okay, we'll do this one, but before we do this one, a way of figuring this out, some of you may have gone like this. You could have said, well, you know what, I know that, so this is how I always figure out the secant. The cosine goes like this, and I have that written right there. And so cosine does a full thing into pi, and then we have pi, and then this right here is pi halves. Okay. Well, what the secant does, since it's 1 over cosine, and I will do the secant in black. So here's x, here's y. So all I'm doing is just recalling the graph of the secant, and this is what we're concerned with right here at x equals pi halves, or theta. Maybe I should be writing thetas. And so, if you remember from trig class, the secant goes like this, and then goes down like that. So I'm just showing you another way of getting this result. And then you have the two bugs walking toward pi halves, and one's going like this, and he's going down, and this guy is going up. Are they ever going to meet? The answer is no, does not exist. So, like I said, some of you might want to not think about what I did here in the cloud, and other people say, no, I'm very good graphing the secant and other things like the tangent and the cosecant, and then this way you just drew the graph and figured it out from the graph. And even though when you're using the graph you're not writing these down, you're kind of doing that when you're following one bug's going up and one bug's going down. Okay, let's do this one right here. I'm going to just try plugging pi in for theta on 1 over cosine. So 1 over cosine of pi. And 1 over, let's see, cosine of pi. Pi is right here, and this is where it hits its minimum of -1. So this is 1 over -1, which gives me -1. So that was just a substitution. You know, if you were looking at the secant of pi is -1. This point right here is -1, so you can get it from the picture as well. So that completes problem number 3. We have one more problem. It has 2 parts, and then we'll be done with 2.4, the infinite limits, which sounds scary at the beginning. Probably for some of you the scariest part was the trigonometry. Okay, so now we have another one where this is different from the last one, because the last one some of you could have said, oh, I can draw the secant of theta really quickly on a graph. And this one, yeah, I don't know if I really want to graph this. So that's why this little, the notation with the 0 and the plus and the 0 and the minus is really going to come in handy. So we have this one. Let's go ahead and plug 0 in for, let's plug 0 in for theta. So I have the cosine of 0 minus 1. This is all over the sine of 0 minus 1. Now if you remember correctly, that the cosine of 0 happens to be 1 and the sine of 0 happens to be 0. So on the top I have a 1 minus 1, which is 0, and on the bottom I have 0 minus 1, which is -1. Now this is not undefined. This is 0 divided by a number. What number times -1 gives me 0? Well, it's 0. So that answers the question. We don't have to consider limits from the right, limits from the left. Let's go ahead and do this one. So this is the cosine of pi halves minus 1. And at any time you could pause and see if you can figure this one out on your own. On the bottom we have sine pi halves minus 1. And so the cosine of pi halves, that happens to be, if you're following the cosine graph, so the way that I always recall these is here's the cosine. This is the cosine of theta or of x, and they want cosine of pi halves. That is 0, so this is 0 minus 1, and over here the sine of pi halves is right here, which is 1. 1 minus 1. So this is -1 over 0. So we don't know what to do with this. So what I'm going to do is I'm going to investigate from the right and investigate from the left. So like I did in problem 3a. So this is the limit as theta approaches pi halves from the right, and this is of our function here. So how is this going to look? When I approach pi halves from the right, the top is still going to be a -1. Well, let's see what the bottom is going to be. This is where we had our problem right here, sine of pi halves. So sine of pi halves gives me 1. Looking at that little tiny picture, I'm going to check. That picture is hardly, okay. I also noticed that the battery on my camera is running out as well. But, okay, it doesn't matter. So, if we're coming to the right, so a little to the right of that hill, we are not at 1 anymore in terms of our height. We're like at 0.99. So think about this. If this was 0.99 minus 1, then that's going to give you a very small negative number like that. So right away you see you're going to get an infinity or a negative infinity, but look, this is a negative number over a negative number, which gives you, see right here. So yeah, we have a -1 on the top and a very small negative number on the bottom. That's going to give you an infinity. There I go, circling it again. Let's go ahead and look at the limit as theta approaches pi halves from the left. And so you have -1 on the top, And on the bottom you're going to have 0, but let's see if it's going to be a very small negative number or a very small positive number. Well, now if you're coming from the left on sign, so sign of something that's a little to the left of pi halves, so this right here is pi halves. Obviously I drew that picture too small. Then you're like at 0.99, because now you're on the other side of the top of that hill. 0.99 minus 1 is a very small negative number. So we're going to get negative 1 over a very, very small negative number. So negative over a negative is a positive. We have infinity there. So all this analysis for what? To figure this out right here. So the limit of g as theta approaches pi halves is infinity. So our answer for this is infinity. And remember in 3a, one was negative infinity and one was positive infinity, so we had to put a DNE. So this is what you do in 2.4. You guys have a good day.